And so we'll move over to the final talk of this session. And I think Aslak, I'm going to probably completely butcher your second name, but Aslak Stubsgaard. So first of all, you win the prize, at least in my opinion, for the most artistic camera image that I've yet seen. Forget the background that I've gone fancy with my background. The fact that you've gone noir.
I've gone full DSLR here.
Yeah. Is that what you're using? You're using the DSLR?
Yeah.
Okay.
Yeah.
It's
1.2.
Awesome. I like it a lot. You win the prize, in my opinion. I'm a keen photographer, so well done. So over to you, Aslak. Thanks very much indeed.
Okay, let's see if I can get this to share. This one and full screen. You can see that?
Yeah, perfect. Thank you.
Great. So yeah, I'm the CTO and one of the co-founders of Copenhagen Atomics. And I'll be giving a brief status report on our development since last year when I presented this workshop. And then also talking about our specific approach towards building molten salt reactor and short-term towards building a 1 megawatt demonstration reactor. So the team was, company was founded back in 2015 by a group of engineers and scientists around the idea of building breeder molten salt reactors in thermal spectrum based on thorium. And the design that we proposed back in 2015 was to use a heavy water moderator that improves the neutronics. The heavy water doesn't degrade like graphite does over time, but we do need special materials to separate the salt and the graphite, or sorry, the salt and the heavy water in order to be able to breed, but we don't need to start with those materials straight away. The heavy water is then room temperature and unpressurized, and it's then being constantly circulated at a high flow rate and cooled and being pumped actively back in, so it would drain in case of a shutdown. That also goes to the salt. We scrapped the idea of a freeze plug and just have the salt go through the dump tank, basically, that is then responsible for decay removal when it's under shutdown. And one of the other ideas we proposed back in 2015, the idea of heavy water was proposed as far back as the aircraft reactor experiment and the program back then, but was that molten salt reactors, by their nature, lend themselves to be miniaturized and put inside of a 40-foot shipping container, or the size of a 40-foot shipping container. And the reason we want to do this is because our whole goal as a company is to produce, mass-produce molten salt reactors on an assembly line, so we can have a reactor that can scale to meet global energy demand in the future. So the idea of the company is just that we build the reactor. We don't build any of the power conversion cycle or whatever the heat is used for. We let the consumer decide that, and we just sell the heat at 650 to 700 degrees Celsius. One of the other things we proposed was to use what we call vacuum spraying, which is basically spraying the entire salt volume just upon leaving the core to extract as much of the volatile fission product as possible, and then recirculate the helium through scrubbers and filters to separate out the fission products. And what we showed is that if we just extract the xenon and krypton just upon leaving the core, because the fission products decay through multiple elements towards the line of stability, we can actually extract quite a big margin, up to like 15% of the fission products, if we capture them while they're being created. If we can then also extract some of the other volatile fission products shown here on the right, we can actually theoretically extract a much larger fraction of the fission products, which is all in the goal of achieving a breeder in the long term. One of the other things we proposed back in 2015 was to use LIPS for online monitoring. One of our co-founders has worked with LIPS for 2 decades, so it was an obvious choice for us, and one of the things we've been working on ever since. But this was the design we proposed back in 2015, but the approach we did towards getting to building one of these reactors has been quite different than some of the other companies. Basically, we looked at the approach of building talking to regulators and going through approval of a paper design. And instead we said that what seems to be the need or the risk of building reactors is more the technology and all the components and systems that have to work together inside of a reactor. So we started, instead of fleshing out our design, we started building all the subcomponents that would go into that design and start building the supply chain to build our reactor. And that's the path we've been on ever since. The goal we also set forth was, before building commercial reactors, to build a 1 megawatt demonstration reactor, or maybe even several 1 megawatt demonstration reactors with different materials and geometries. And we see this as an approach where we can move faster in the beginning and test all the components with inexpensive stainless steels and inexpensive salts before we ever get to any nuclear part, where we have to involve regulators, and where any change or the thing that we have to alter becomes very expensive. So that's the road we're on. And earlier this year, we then got a fair amount of funding to build a non-fission prototype for the next coming 2 years. And so if we look at a timeline, we started building and selling these loops all the way back in 2017. And here in 2019, we had basically all the components we need for a bare bones boilerplate non-fission prototype. And so this non-fission prototype is basically a 1-to-1 scale of a 1 megawatt demonstration reactor that fits inside of a 40-foot shipping container. And it has all the same features, but scaled back. So for example, the vacuum spraying we talked about, we might not implement that yet. It's all the key components like pumps, core, the heavy water, and the separation materials. They might just be stainless steel in the beginning. And it might be the heat exchanger and the dump tank. So basically just the bare bones minimum of what a 1 megawatt demonstration reactor. And only when we've built and tested that will we then decide on what country to test it in. We're already talking to some facilities and countries about testing this reactor at their facilities, but we're looking at multiple options for testing it. And the salt we're looking for using here is a lithium fluoride, thorium fluoride, and hopefully starting on plutonium. But if we can't get our hands on that, we'll go fine with just enriched uranium. And so you might think that this is trying to build something similar to what they did in the MSRE, but it's actually more akin to what they did in the aircraft reactor experiment, which was they built a 2.5 megawatt thermal molten salt reactor, where you see the core geometry on left, a small size, and they only operated for a couple of weeks. And we also, if we can only get approvals to operate it for a couple of weeks, that's what we'll do, but probably up to a couple of months if we're allowed to. The key difference being, of course, that we want to use heavy water and then insulation material between the salt tubes. And yeah, we would like to use silicon carbide here, or silicon carbide composites, or some other variants of that. And we're looking and testing several options, but if we can't get it approved in time, we'll just use stainless steel for the brief life of the reactor. But this is also similar to the approach that they took in the MSRE days, and before that in aircraft reactor experiment days, which was to build a bunch of loops and test the components before you ever get to building a reactor. And even in the MSRE days, here you see like one of the fuel pump loops, test setups. And on the right, you see a flow straightener that dislodged and got cut into the impeller eye. And that's just to say that even after decades of experience, you still have components failing on you and stuff breaking. And that's part of the course. And that's why we do testing before we start turning a reactor on. And even after the MSRE days, we're still having these giant buildings filled with loops. So this is sort of similar to what we're trying to do. We're making the loops a lot more compact. If you saw before, there was a lot of piping between the different components. Where our approach is more to make it the same design ideologies as our containerized reactors, basically have all the electronics and heating system, gas system management inside of a tight containment. And you see here some of the loops we built since 2015, sort of iterating. The first one was a pressurized fed loop, and some of the second ones here or the first pump loops. And now we're currently on our 5th generation of loops you see here over on the right, which has more or less the same capabilities as some of those loops you saw at Oak Ridge, just compressed down a lot more. we're now at the point where we feel that we need a lot more of these loops, and we're happy with the design, so we're scaling the production of them. And here you also, on the right, you see we're building some other systems that is a 500 liter solar salt loop. And what allows us to do this is basically our pump, which is a canned rotor pump, so that's very different than the cantilever type pump they had in the MSR days, which is basically you have a pump at the bottom, you have a long shaft and a dynamic seal, and then you have a motor at the top that you keep cold. Where this design is basically, it's all compressed into a canned rotor pump, so that means that the rotor and impeller are together, and then they're actuated electromagnetically, and that allows us to just weld the whole thing up and not have any dynamic seals. And we're currently looking at building a version of this with electromagnetic bearings, and that basically allows us to also levitate the impeller and rotor assembly on an electromagnetic field, so we don't have any wearing surfaces. And with that, we actually expect to get something like 10 years lifetime inside our reactor without any maintenance or service, because there's no contact area besides the salt. And yeah, so this is what we're doing. We're basically testing and building all the small subsystems that we need to put inside of a 1 megawatt demonstration reactor, but first for our non-fission prototype. And here you see some of the different components we're testing: heat exchangers, our newer pump and filters, valves, tanks, gaskets, that sort of stuff. And this is just showing some roughly where the different components would fit inside of a 40-foot reactor design. And yeah, so we're located in Copenhagen along with the facilities of Alfa Laval. Alfa Laval is one of the world's leading manufacturers of heat exchangers. And the reason we're located here is also because we're looking to use one of their plate heat exchangers up to 700 degrees C. So it's an all stainless steel brazed plate heat exchanger that we expect to be able to use in our reactor and actually get a lot more efficiency out of that compared to classic shell and tube heat exchanger. I'll show a brief video here of some of our different setups. So the loop I mentioned here before, it's basically a fuel salt loop inside the furnace that is then encapsulated in another shell. And both of those containments then have argon inert atmosphere. And then we have an air conditioning to keep all the electronics and actuating and VFDs cooled. Then you see here our older version of pump inside the loop. And that's basically where we can put in different components and pump salt around, run different tests with the different kinds of salts. We always start with the testing with the water, and then we move on to nitrate salts, which is also what they use in the solar power industry, but that has a limit of 560 degrees Celsius. But we start with that, and then we move on to FLiNac, which is our main testing salt for fluorides. And you see here an ingot of one of this. We produce in these 1 kilo batches where you have to purify them before we can put them in the loop to eliminate more moisture and oxygen and other contaminants. Here you see one of our other loops pumping the salt. And if we turn the light off, this is one of our pressure-fed loops with FLiNac at 700 C. And you can see it's glowing red hot when you adjust for the white balance. And yeah, this is just showing one of those nitrate salts from before, basically showing how the viscosity and like the general fluid characteristics is very similar to water. And the nice things about the nitrate salts is that they allow you to test things without needing that inert atmosphere, and it's a lot easier to handle. They have lower melting points, so you can start testing with those. And as you see here, they're very easy to handle and very much similar to water. But as soon as you tested your equipment, your valve, your filter, whatever it is, then we usually go on to FLiNac and test with that. And being here at Alfa Laval in Copenhagen, it's a giant, basically manufacturing facility where they create food and water systems. We have a bunch of offices and workspace and labs. And here I'm just showing some silicon carbide tubes at 900 degrees Celsius. We're getting tubes from different vendors and then completely stress testing them by dunking them into room temperature water at 900 degrees C to see what would happen basically. This is, I guess, simulating a worst case accident in one of our cores if water spilled in past its containment into the insulation layer and directly onto the silicon carbide. So yeah, this is some of the stuff we do here, I guess. And yeah, we use Alfa Laval a lot for assembling basically our loops. They have a lot of welders and machinists, world-class machinists and welders that we basically source all these parts, forged, investment cast, stamped, molded parts, and then assemble them here in Copenhagen and build these loops from them. I think we have something like 200 plus suppliers that we built over the past 5 years. So yeah, I guess we can move on. So this is the roadmap for us. Basically, we're trying to make a minimal viable product in terms of a test reactor, and only put in the features that we can get done and that we feel confident will work inside a reactor before we ever move on to building any sort of larger scale 100 megawatt. And only after that, in the 2030s, we look to commercializing these reactors and build them on an assembly line and mass manufacture them. This fall here, Alfa Laval closed down a lot of one of their manufacturing halls. So basically, this whole space here we've started renting and moving into, and we also, you can see some of our loops there on the right. We basically hope to have this whole room filled up with the loops within the next year. And so if you're a molten salt tinker out there who is looking for a job, please write to us. On the right, we also bought a laser welder recently that we're going to install there to manufacture some of these more challenging parts with higher needs for this molten salt environment. We also got approval earlier this year to run some of these loops with fertile salts outside of Denmark. I can't say which country yet, but we're basically preparing for that by starting with some stagnant salt tests. So we have 3 different test setups, which is basically preparing to run with the fertile salt test, but we'll ship them out soon and do those kinds of tests. But this is basically all the electronics, valve acquisition we need to test flanges and just basic corrosion before we start pumping salt that is fertile in one of our loops. And I guess this also caught the attention of the IEA earlier, because last 2 weeks ago we got a safeguards visit from the IEA from inspectors that took nice samples and made sure we weren't doing anything we're not supposed to, which of course we're not. But yeah, that was a very friendly visit. And lastly, I would say that as part of this selection of where to build our first demonstration reactor, we're supporting this petition to build it in the Netherlands. So if you would support that, go sign that. Questions?
Excellent. Thanks. Thank you, Aslak. So we do have a couple of questions. The first one is, what's the maximum temperature on the canned pump?
Let me stop sharing here. It's basically 700 C. It's whatever the material you use. We use stainless steel. So if you go 700 C with stainless steel for a long time, you might have some issues. You could build it out of other materials, but that's going to cost more and take longer time. So we don't need that right now. We just need something that works well enough. Okay. So that's why everything is stainless steel 316.
Okay. The second question was, are the new MS systems from Copenhagen Atomics equipped with flow measurement devices?
We're working on flow sensors. It's not a high priority for us, but we have some different ideas and we have some tests in the making. But yeah, if you want to collaborate with that with us, give us a message, and that's one of the things we're working on. And we're happy to collaborate with the universities, labs, other companies. We need to work together to build these reactors.
Excellent. And just
I didn't say we also sell these loops commercially, starting at 88K. So that's a bargain.
Okay. And just a question from me: why, if you can elaborate on why the Netherlands of all places? Why is that the right place?
There's always been a lot of support in the Netherlands for molten salt reactors, and they have facilities there that are approved to have certain kinds of nuclear tests. So we see it as a possible place. It's not the only likely place. We're also looking to the US, of course, but also other places.
Okay, so the Netherlands is somewhere like NRG at Petten or somewhere like that because of their
Yeah,
work.
that's one of the promising places.
Okay, understood. That makes a lot of sense. Well, thank you very much. There was no more questions, so thank you very much for your time. Great talk, and appreciate the black and white image as well. I'm going to try and do that for my own cameras in the future. Inspired me. So thanks, Aslak. So that concludes the session for this afternoon on the fuel cycle.